If you're subscribed to this channel, you've probably noticed I've taken a deep interest in long-range low-power radio, or LoRa. For my purposes, LoRa could be helpful with remote flow detection for stormwater sampling, which is something required by my agency for evaluating non-point source pollution. Having said that, it also has other intriguing applications. For example, Amazon has already picked up on LoRa's possibilities via its sidewalk push. Recent software updates to Echo devices now turn those personal units into small LoRa gateways to the internet, which can be used for tracking tags on things like pets or wallets by taking advantage of your home internet connection. Of interest, Amazon shares your LoRa-enabled hardware with anyone that has sidewalk-enabled tags. Now, if your spidey senses are tingling, it's probably warranted given that Amazon turns these features on by default without your consent, and you have to manually turn them off if you're concerned about privacy. Essentially, Amazon is offering a free service that relies on your internet connection, albeit a small slice of the same. So I'll leave it by including a link in the description of this video if you have an Alexa-enabled device and would like details on how to turn this feature off. In addition to Amazon's Sidewalk and the Things network, Helium is another player building smart networks, and one that's growing rapidly through the use of cryptocurrency to incentivize the creation of hotspots. Although many of the technical details I've shared on this channel apply to Helium gateways, note you have to have a gateway that's been blessed by Helium to participate in harvesting Helium tokens, and those can be very difficult and expensive to come by, at least as of the time of this writing. An area I'm interested in with respect to LoRa is farming. My brother-in-law, who is a farmer, has given me a first-hand account of some of the monitoring challenges that farmers deal with. Everything from needing to know how much it rained on a remote field to monitoring soil moisture conditions over time. Soil moisture is especially important in the state where I live, where farmers augment seasonal rainfall with deliveries from the Central Arizona Project for crop irrigation. Imported water from Lake Mead via the CAP has turned Arizona into an important agricultural resource, but this also comes with challenges. Due to an exceptional drought in the southwest, Lake Mead is at historic lows, and deliveries of CAP water are likely to be diminished. With Arizona farmers being first in line for cuts, and with overall state allocations decreasing as water levels continue to diminish over time. This will surely put more pressure on groundwater resources in my state, which will only compound impacts from overdrawn aquifers, resulting in challenges such as land subsidence. Monitoring soil moisture conditions remotely using technologies such as LoRa could help us with smart irrigation. This certainly isn't a solution to Arizona's water supply challenges, but it certainly could help us use our precious water resources more efficiently. In this regards, curiosity about the potential of LoRa to transmit data in agricultural settings is a perfect foundation for field tests. So, while on vacation visiting my in-laws in the Midwest, I decided to dust off some old LoRa hardware from older experiments to support telemetry tests in farmland. The topography where I'll be testing is flat, similar to what we have in Arizona, but with a great deal more water. The overall goal is to see what kind of telemetry I can realize in flat farmland, common to northern Ohio and Arizona. For the transmitter, I'm using Adafruit's RFM95 LoRa Packet Radio Breakout attached to an Arduino. Adafruit has put together a nice tutorial for this board, which I'll link to in the description of this video. This tutorial is for both the RFM69 and RFM95 radios, so don't let the title on this page confuse you. The tutorial provides a fritzing diagram using an Adafruit Metro, but you can substitute an Arduino Uno for the same. For the receiver, I'll be using an Adafruit Feather MO LoRa radio, which I'll be combining with a Feather OLED to facilitate reading data in the field. There's no wiring involved in the case of the Feather MO LoRa receiver. Just stack these in the doubler and you're done, but do make sure to solder or attach an antenna to this board before powering it on, or you risk destroying the board. That goes for the transmitter as well. The Adafruit tutorial will point you to libraries and code for setting up your transmitter and receiver. The code I used was from what I suspect was an older Radiohead library, so it's likely to be different from what Adafruit points you to on its tutorial, but it worked fine. To ensure full transparency, that code that I used is available on my website as a zip file under this chapter. Adafruit notes that you must take care to properly define your pin mappings in order to get your transmitter and receiver to work properly. I've done the same in the code shared on my website. Adafruit also reminds you to properly set up the frequency for your radio, as I've done in the code for my region. Finally, Adafruit notes that you need to set your radio transmission power in code, taking into consideration trade-offs between power and range. Adafruit also highlights the need to set the second function argument in the power function to true. For the test shared in this video, I uploaded code downloaded several years ago and consequently missed this guidance. My instinct was telling me that this could result in transmission power defaulting to 13 dBm. I contacted Adafruit for confirmation and was informed that the associated Boolean true guidance is only for the RFM69, not the RFM95 that I was using. As such, my code was okay for realizing the maximum dBi for this breakout board. I only mention this here in the event others get similarly confused. Set the Boolean flag to false if you try to recreate these tests with the RFM95 breakout board. In order to make my receiver mobile so that I could easily mount it to a bike rather than monitoring telemetry on a serial monitor via my laptop, I included an OLED screen and modified the receiver code to report RSSI to that screen. This allowed me to strap my receiver to a bike so that I could cover more ground for my tests. This, coupled with the GPS capabilities of my iPad, allowed me to easily map my telemetry during my survey. You'll also notice that I used a wire antenna on my receiver rather than the store-bought antenna. This is so I could test the native telemetry capabilities of the receiver without any help from a commercial-grade antenna. This was not the case for the radio transmitter, which uses a 2 dBi antenna purchased from Adafruit, reflecting the setup I had available to me at the time I did these experiments. Given the importance of line-of-sight to telemetry, I should mention the transmitter is located about 6 feet off the ground, whereas the receiver will be tied to a bike rack with an elevation of about 2.5 feet, judging from the 27-inch diameter wheels. With respect to RSSI response, I anticipate seeing a range from -40 at close proximity to -129 at distances pushing the limits of telemetry. Okay folks, so I went ahead and I just mounted the transmitter on this clothesline outside my in-laws' house. You can see the antenna is nice and straight, there's nothing obstructing it, and this is just to kind of give you a 360 view of what things look like. Nice and flat, except for a highway out there in the distance. But I'm going to take a ride along a bike trail and see what kind of signal response I can get from my receiver. Okay, and there's the receiver mounted to the back of a bike. There's the transmitter out on the clothesline. Let's see what the RSSI is. Nice and close to the transmitter. So it's pretty good, as you'd expect it to be. Okay, and I just exited the driveway. You can see that my RSSI, relatively close, is about -74. Now I'm going to head down that way and I'm going to hit that bike trail. Okay, I'm at the start of the bike trail. RSSI is -80 and the transmitter is behind the Kwanzaa barn back there. Lots of vegetation here to create all kinds of path loss. I should get some interesting results here. Okay, there's an opening in the bike trail. I'm not very far from the transmitter, and my RSSI at this location is about -87. Okay, I'm still on the bike path. I'm actually right underneath this overpass for this bike path. And there's a lot of vegetation, a lot of trees, and a lot of dirt between me and the antenna right now, the transmitter. Let's see what I've got. And the RSSI here is about -106. So still acceptable for transmitting data. Pretty amazing that I'm in this tight little area right here and I can still get a signal. Okay folks, I must be at least a mile away from that transmitter. I'm well beyond that overpass. I'm close to the next major intersection for the bike trail. And I still have RSSI that's workable here at about -114. -129 would really be pushing the limits, but at this location, looks like I still be able to transmit some environmental data. Okay, I'm starting to get into the woods here, so I thought for sure by now I would have lost telemetry with my transmitter, but it looks like it's still working. -128, so I'm really kind of pushing the limits here. You can see it's supposed to be sending every second or so, so this might be about the extent of the range that I can manage, at least in this direction. Okay, I'm back, pretty close to where I started. The transmitter's behind that. Transmitter's behind those trees in that barn that's kind of hidden between those trees, and yet I still can get telemetry out here. It's coming in, let's see, at about -103, probably because I'm standing in the way, -88 or -89. So that's pretty impressive considering what that telemetry has to shoot through right now. That's the road I just rode up. I'm gonna head in the other direction now. I'm gonna go down this way and see what happens. Okay, I just rode down just a little ways through some vegetation. The transmitter is behind these trees and this cornfield off in that general direction over there. I've got a pumpkin patch, I believe, over on this side. Maybe they're growing beans here, I'm not sure. I know those are pink pumpkins down there. In any event, the whole reason we're here, let's see what's going on. RSSI is -102 at this location. Okay, I'm at my next road crossing, and the RSSI at this location is about -117. Let's see if I get out of the way. -124, -120, and the transmitter is way off in that direction, behind that cornfield and to the left of that house. All right, I'm at my next park bench along the bike trail. You can see that it's really beautiful out here. These trees are just amazing. Let's take a look at what the telemetry is from this location. And right here you can see that I am having a little bit of trouble realizing telemetry. It should be pinging it about every second. Let's see what happens if I just relocate a bit. I'm at about -124, so not bad. I'd still be able to realize a little bit of telemetry from this location. And of course, the transmitter is way down the road behind all this vegetation out here. Okay, I'm at my next road crossing here along the bike path. Just to kind of give you a lay of the land. And at this location, it looks like I'm out of luck. I'm not realizing any telemetry on a 1-second interval. I bet if I could get my transmitter up one of these power lines or give it some elevation, I'd be able to shoot through this vegetation no problem. But the path loss might just be a little too much for this location. So I know that if I go up about 100 yards in that direction, I'll be able to ping the transmitter again. but not here. Okay, I decided to head up this road in this direction, which has gotten me outside of that wooded bike trail where all that path loss was being realized, I'm sure. And it seems like doing so actually helped me restore my telemetry. It's marginal. I'm at about -125, -129. But getting out of that wooded bike path really helped, because I have telemetry once again. So I'm not shooting down that alleyway of vegetation and realizing all that path loss. And I couldn't help but notice this cell phone tower out here as I was heading back to the bike path. And I bet if we could get one of our little LoRa WAN gateways installed on a cell phone tower up there, we could probably see for miles out here. I mean, keep in mind that I'm shooting all the way out here through all this vegetation from a little radio that's being powered by 4 AA batteries, and I can still manage to get pretty far out regardless of all this path loss. So imagine what we could do if we could get a LoRa WAN gateway on a cell phone tower this high, elevated above an area like this that's so flat. We could probably see for miles and miles. And I thought I'd stop quickly and just take a picture of one more interesting feature out here, having to do with these ditches, which my in-laws tell me were used to basically drain this area, which was historically a swamp. And draining it apparently resulted in a lot of black soil being ideal for farming out in this part of our country. So there you have it. So while on my ride, I came across this really interesting cemetery on off one of the roads off the bike trail. I wouldn't be surprised if I had some relatives who were buried here on my wife's side. Anyway, I thought this would be an interesting spot to take a look. And yes, I do have telemetry here at about -112 RSSI, shooting through the cornfields and the woods off in this direction. And I'm just about back home. And you can see that I'm getting telemetry here about -99, -98. And the telemetry at this latest intersection of the bike path is taking place with the transmitter that's behind that gray building between those trees. And just for grins, I wanted to show you this pumpkin field, which kind of makes me wonder what this place is going to look like during Halloween this year. And I've always wanted to see what a real pumpkin patch looks like, and I think this is it. Pretty neat. And there's our transmitter. And you can see that it's only about 6 feet off the ground. So all that wonderful telemetry that we realized behind that overpass through all these woods was managed off of something that's relatively low off the ground. And I think the thing that Ohio has going for it is that it's so flat out here that the only path losses you really need to deal with are vegetation. And at this location with the transmitter so close to the receiver, you can see that we've got an RSSI of -42. For the next test, I moved the antenna to an old tree stump adjacent to a road in order to evaluate telemetry along that road. I should mention the transmitter is now located about 5 feet off the ground. And you can see that the RSSI at this close location is, I don't know if you can read that, well, it's about -50. All right, so I hit my first stop sign, and it's a little too bright to see the display on that, but I'm looking at about negative 103 RSSI at this location. Okay, I'm a little further down the road. You can see the stop sign that I was just at, where that car just turned. I'm like right next to this big cell phone tower, so I figured this would be an appropriate place to check up on things. Let's see what we got. And it looks like it's about negative 115 at this location. All right, I came up on this cornfield right here, separated by these beans. I thought this would be a nice place to stop just to kind of give everybody a lay of the land. You can see how flat everything is out here, which certainly helps. But at this location right here, I don't have any telemetry. And we're back at square one. So I wonder what would happen if I put this thing on a ladder. I wonder if I went back to that location, if I'd be able to read it. So I'm gonna ask my father-in-law if he's got a ladder I can play with. To help improve telemetry, I elevated the antenna to 8 feet off the ground. So I got this ladder from my brother-in-law. I just leaned it up against this old wood stump, and now I'm gonna head down in that direction. And I think you can kind of get a general idea of how much distance I got. There's that cell phone tower way in the distance, which was a little bit before the limit of where my telemetry cut off last time. So let's head back. There's the path I was on yesterday, and there's the pumpkin field I pointed out. All right, I'm back at the first stop sign. Let's see what my RSSI now is, just for comparison. Looks like it's about negative 109, so I think that's a little better than what I had before. That's the direction I'm headed. All right, I'm about halfway between that cell phone tower right there and the edge of the cornfields down the road. And I am getting telemetry at this location. I'm at about negative 123 RSSI. So let's see if it holds. And I'm back at the cornfield boundary. You can see it right there. And no luck. Didn't really help too much having that elevated only a couple feet. Probably need to elevate it more like 20 feet to really make a difference here. But in any event, it was interesting. I think what I'm going to do is maybe head to that stop sign over there, head right, and see if that will pick up anything, because there might be houses or vegetation or something that's impacting line of sight at this location. And I just made a left off that stop sign. That's the bike and the receiver. You can see where the cell phone tower is located. And sure enough, I am getting telemetry at this location. It's coming in at negative 117. So there was definitely something at the edge of that cornfield that was interrupting line of sight. I see a lot of homes, a big barn. Probably had something to do with it. So it just demonstrates how important line of sight is for LoRa. With that said, I'm going to keep going down this road and just experiment with how far I can realize telemetry off this very modest setup. Okay, that truck over there is the stop sign that I just turned right on. And sure enough, I've dropped in elevation. I'm behind this little cornfield right there. And I don't have any telemetry at this location. So this tells me that just a little bit of of terrain or a little bit of contour in the landscape can certainly have an impact if you don't have some elevation on your antenna. So you can probably buy a really nice antenna, spend a lot of money on it, but if you don't put some elevation on it, it's probably not going to do much better than a little $10 antenna from Adafruit. Okay, and while riding, I noticed the highway over there, and I know I'm right on the other side of that little highway. So I decided to see if I had any telemetry at this location, and sure enough, I've got about negative 115 RSSI from this spot. So I'm about 1 mile away from the bike trail that I was hitting yesterday, the north end of the bike trail. And telemetry is pretty marginal here, but I am getting telemetry at about negative 129 RSSI. All right, I'm back at the northern end of the bike path. This used to be an old railroad track, or so my in-laws tell me. So that's the way the railroad used to go. They've turned it into a bike path, which is really cool. Same bike path I was on yesterday. No telemetry at this location. So I'm going to start heading back home along this bike path and see where I can pick it up. And as you can see, it's really beautiful through here. Seeing all kinds of deer, fawns, beautiful birds, picked raspberries off the side of this road. Very different from where I live in Arizona. It's nice and cool through here. It's really a nice place to take a vacation. And this is one really cool thing about visiting this place is I get to see bumblebees. I just don't see these much anymore in Arizona or in California where I grew up. But there are quite a few out here. Not as much as there used to be according to my in-laws, but still, seeing a few is kind of a rare treat. Look at that guy go. Gotta watch out for the poison ivy. Yum. So good. And the RSSI at this location is about right on the margin, negative 128. So this is about the extent of coverage, at least on the bike path shooting through all these trees. I thought I'd stop a minute here along the bike path and point out this little wetland that used to be farmland. This belongs to my father-in-law, and he worked with EPA to set this aside to just let it go back to its natural conditions. And he tells me it's been like this for about 20 years. You can really see how Mother Nature comes back if you just leave it alone as a kind of like a little nature preserve, I guess. So it's pretty cool. And while we're at it, I'll just mention that the RSSI here is about negative 107, even with the bike sitting behind all these trees. And the radio is located behind that house back over there. And there's the radio, right where I left it. So I'm going to do one last experiment to test the attenuation of a brick wall on the radio signal. I'm going to go into my in-laws' garage. I'm going to check RSSI outside and inside to see how much is attenuated by structures. Let's see what I got right here with good line of sight. It's about negative 57. Negative 56. Now I'm going to take it into the garage. And it looks like it's about negative 83. So that goes to show you how much attenuation you can get from a structure. So here are the results of the field experiments tabled. Keep in mind that these results are for a 100 milliwatt transmitter with a 2 dBi antenna talking to an Adafruit Feather LoRa MO with a wire antenna, with the transmitter elevated 5 to 8 feet off the ground and the receiver elevated about 2.5 feet off the ground. Also note that these experiments took place in a flat agricultural setting with path loss introduced from trees, barns, and homes. It's interesting to sort this data on distance transmitted as well as RSSI. When sorting on distance, you can immediately see the effect of path loss interfering with some closer survey points, while still allowing me to realize telemetry at farther distances where path loss may not be as great a factor. On this note, line of sight without interference is probably more important than purchasing an expensive antenna when trying to realize cover. This is further corroborated when you note that poor RSSI can sometimes take place at relatively closer distances, again suggesting that line of sight is key for coverage. I realize that these are well knowns within the LoRa and ham radio community, but it's interesting to experiment with these receivers and see these conclusions play themselves out firsthand. With respect to using LoRa to transmit remote environmental data like rainfall or soil moisture in agricultural settings, it's clear there's potential for helping us manage our water resources more efficiently using low-cost hardware and radio frequencies licensed by the FCC. In fact, I'm certain this has already been done by commercial outfits, although I haven't researched this in depth since I prefer developing custom solutions using off-the-shelf hardware. And I also enjoy sharing these ideas for anyone who can't afford hiring a consultant. So that's about it for this chapter. I hope you enjoyed it. Subscribe for updates. Eventually I'm going to get around to finishing up that installation at ZeroCraft and also figuring out how to get actual data posted to the Internet of Things, which is really what this is all about. All right, thanks for watching.